AI Security Vulnerabilities and Exploits. Anthropic's Red Team made a post this week. Claude Opus 4.6 can discover high-severity zero-day vulnerabilities in open-source software, out of the box. No custom scaffolding, no specialized prompting, no task-specific tooling. The editorial, authored by Nicholas Carlini and colleagues, reports that the model has already found and validated more than 500 high-severity vulnerabilities, with initial patches landing in affected projects. What makes this noteworthy isn't just the number, it's that these bugs were hiding in some of the most heavily fuzzed codebases on the planet, projects that have accumulated millions of CPU hours of traditional fuzzing over years. The key difference between LLM-based vulnerability discovery and traditional fuzzing is architectural. Fuzzers work by hurling random inputs at code and observing what breaks, a brute force approach that excels at finding certain crash-inducing bugs but struggles with logic flaws. Claude Opus 4.6, by contrast, reads and reasons about code the way a human researcher would, examining past fixes to find analogous unpatched bugs, recognizing problematic patterns, and constructing precise inputs that trigger failures. The Anthropic team argues this creates an inflection point for AI's impact on cybersecurity and frames their work as a race to empower defenders and secure as much code as possible while the window exists, the implicit concern being that offensive actors will eventually wield similar capabilities. The focus on open-source software is strategic. These projects run everywhere from enterprise systems to critical infrastructure, yet many are maintained by small volunteer teams with no dedicated security resources. The timing is ironic given what security researchers at Wiz found when they turned their attention to Moltbook, the viral AI agent social network that Andrej Karpathy once described as genuinely the most incredible sci-fi takeoff adjacent thing I have seen recently. A routine, non-intrusive review, simply browsing the site as a normal user, revealed a Supabase API key exposed in client-side JavaScript, granting unauthenticated access to the entire production database. The haul: 1.5 million API authentication tokens, 35,000 plus email addresses, 4,160 private DM conversations, and plaintext OpenAI API keys. The platform's founder had openly acknowledged that he vibe-coded the entire thing without writing a single line of code himself. Perhaps the most deflating discovery was that Moltbook's claimed 1.5 million AI agents mapped to just 17,000 human owners, an 88-to-1 ratio, with no mechanism to verify whether an agent was actually AI or just a human running a script. The revolutionary AI social network was largely humans operating fleets of bots, the researchers concluded. The Moltbook saga didn't end there. Separately, researchers at Depth First discovered a critical one-click remote code execution vulnerability, CVE 2026-25253, in OpenClaw, the open-source AI personal assistant formerly known as Moltbot and ClaudeBot, already trusted by over 100,000 developers with access to iMessage, WhatsApp, Slack, and unrestricted local computer control. The exploit chain was elegant in its simplicity. Clicking a malicious URL silently overwrote the gateway URL in the application's settings, which then automatically bundled the user's authentication token into the handshake with the attacker's server. From there, the attacker had full access to the victim's instance, reading messages, executing actions, stealing credentials. When you grant an agent God mode permissions, as the researchers noted, the margin for error vanishes. Local LLM Optimization and Performance. While Anthropic pushes the frontier of what massive models can do in the cloud, a parallel community continues to squeeze every last token per second out of local hardware. A clever approach, gaining traction on the local llama subreddit, treats inference optimization as an automated experiment rather than folklore. The method is simple. Hand a coding agent a prompt asking it to systematically benchmark all relevant llama.cpp toggles for a specific model, log the results, and generate an optimal runner script. The poster shared detailed results from testing GPT OSS 120B on an M1 Ultra with 128GB RAM, and the findings illustrate why tune once globally is fundamentally wrong. The benchmark results are instructive. Flash attention yielded an 8% speedup, 67.39 to 72.76 Tecan. KV cache format choices produced wildly divergent results. F16 was fastest at 73.21 per second, while the Q8 F16 combination was catastrophic at 19.970. A disaster, the author flagged. Disabling KV offload cratered performance to 25.84 T, a 64% slowdown. Batch size variations, by contrast, barely moved the needle. The combined best configuration delivered 8 to 12% higher sustained tokens per second over default settings with zero quality regression. The key insight: different models respond differently to these toggles. So per model, per machine tuning is essential, and letting an agent enumerate the parameter space turns this from guesswork into reproducible science. The local AI ecosystem continues to expand in other directions. A developer used Claude and Kimi K2.5 in an agentic loop to implement Qwen 3 ASR 0.6b, an automatic speech recognition model, in pure GGML, roughly 12,500 lines of C++ generated with minimal human guidance. With Q8 quantization, the model runs under 2 GB of RAM, including the forced alignment component for word-level timestamps. Meanwhile, another developer demonstrated running LLMs and vision language models fully on-device on iPhones with just 6 GB of RAM, using metal acceleration for offline inference. Models like Qwen 2.53, Gemma 3, Llama 3.2, and Small LM deliver text responses in 1 to 2 seconds and image analysis in 2 to 3 seconds, with careful context window management and quantization, keeping everything within mobile memory constraints. Privacy-focused AI applications and tools. The push toward local inference naturally dovetails with privacy concerns, and a new open-source project called ClawGPT attempts to address the gap between powerful chat interfaces and user data sovereignty. The tool connects to models through OpenClaw, the same platform that just had a critical RCE vulnerability disclosed, a fact worth keeping in mind, supporting anything OpenClaw can talk to, including Claude and local models. The feature set targets power users who find existing UIs limiting, editing any message in a conversation, not just the last one, conversation branching to explore different reasoning paths, mid-conversation model switching, semantic search across all chats, and full export-import capability. The most technically interesting aspect is the phone-to-desktop sync, which uses end-to-end encryption via TweetNaCl with X2559 key exchange and X-SALSA 20 Poly 1305 authenticated encryption. The sync works through an encrypted relay where the server never sees plain text. You scan a QR code from the desktop, and the phone becomes a thin client. The project is deliberately minimalist in its tech stack: plain HTML, CSS, and JavaScript with no build step, no node modules, no React. All data stays local. The project is MIT licensed and self-hosted. A related project, OpenClaw Assistant, aims to be a privacy-first Android voice assistant with OpenAI-compatible API support, though community reaction was skeptical. As one commenter put it, OpenClaw and privacy don't belong in the same sentence. Given the CVE 226-25253 RCE chain disclosed this same week, that skepticism seems well earned. AI-powered development and coding tools. Steve Yegi, never one to bury the lead, introduced us to Gastown, an IDE paradigm for 2026 that he describes as an orchestration system for managing 20 to 30 Claude Code instances simultaneously. The concept is what happens when you take the current wave of CLI-based coding agents, Codex, Gemini CLI, AMP, Amazon Q, and ask what comes after cloning them. Yegi's answer: lashing Claude Code camels together into chariots. The system is architecturally comparable to Kubernetes and Temporal, managing parallel AI agents with supervision hierarchies, merge queues, workflow orchestration, plugins, and quality gates. Yegi presents an 8-stage framework for developer evolution with AI, from basic code completions, stage 1, through full agent orchestration, stages 7-8. The current codebase is under 3 weeks old, written in Go, and in a detail that will either inspire confidence or existential dread, is 100% vibe-coded. Yegi claims he has never personally reviewed the code, drawing a comparison to SourceGraph Cody's 225,000 lines of Go used by tens of thousands daily. As a technical proof point, Gastown solved the 20-disk Tower of Hanoi with a 1,000,000-step procedure, contradicting research, the Maker paper, claiming LLMs fail after a few hundred sequential steps. Whether this generalizes beyond well-structured recursive problems remains to be seen. but the ambition is clear. The future of coding isn't one agent in a terminal, it's a fleet. The question of how far AI-assisted development can stretch into regulated domains surfaced in a pointed Reddit discussion about vibe coding for healthcare applications. The community consensus was brutal. The top-rated response: if you want a life-altering lawsuit on your hands, vibe coding in healthcare is the speed run. Multiple commenters invoked the Therac 25 radiation therapy disasters of the 1980s, where software race conditions delivered lethal radiation doses. A commission attributed the cause not to specific bugs, but to generally poor software design and development practices, language that could describe much of today's vibe-coded output. The practical advice: use AI for prototyping and internal tools, but anything touching HIPAA-regulated patient data needs rigorous engineering discipline. On the more optimistic end of the spectrum, an OpenAI researcher shared that he spent $10,000 on Codex API costs in a single month and considers it totally worth it. His setup is deliberately simple: Git worktrees, multiple shell windows, and one VS Code instance per worktree. The key insight was getting Codex to continuously document and improve its own workflows, committing notes and helpers to a personal folder in the monorepo. After a few interactions with any part of the codebase, these self-generated helpers stabilize and compound across sessions. The researcher uses Codex for extensive due diligence on experiments, exploring Slack channels, reading discussions, fetching experimental branches, and cherry-picking useful changes, creating a high-recall search agent for settings where mistakes are costly. Meanwhile, developers are already finding practical value in running multiple AI models in tandem. One user described passing Claude code output through Gemini CLI for secondary review, catching errors that either model might miss alone. Cybersecurity infrastructure and supply chain attacks. The security landscape extends well beyond AI-specific vulnerabilities. eScan, an Indian antivirus product from MicroWorld Technologies, suffered a supply chain attack when hackers compromised an official update server, distributing malware to enterprise and consumer endpoints globally. The irony of antivirus software delivering malware is not lost on anyone. Security firm Morphosec, which detected the malicious behavior on January 20th, reported that the rogue updates deployed a multi-stage infection chain. A malicious reload.exe modified the host file to block future legitimate updates, established persistence through scheduled tasks, and downloaded additional payloads. Critically, automatic remediation is impossible for compromised systems. Affected organizations must proactively contact eScan for a manual patch. The vendor response was characteristically defensive. eScan confirmed unauthorized access, but downplayed the incident, objecting to the supply chain attack label while simultaneously acknowledging that an incorrect file was placed in their update distribution path and distributed to customers during a limited time frame. Their own advisory describes system behavior consistent with Morphosec's findings, and the company rated the impact as medium-high for enterprise customers. The incident reinforces a pattern. Trusted update infrastructure remains one of the most valuable targets in cybersecurity, precisely because it bypasses every perimeter defense by design. Strix, an open-source agentic security platform, surfaced this week with a mission to help teams identify exploitable vulnerabilities through AI agents that run continuously as applications evolve. The project positions itself as producing less noise, more actionable remediation guidance compared to traditional scanners, with an evaluation harness, Strix benchmarks, for measuring agent performance. The tool joins Pentest Agent in a growing category of AI-powered security testing frameworks, a space that's rapidly filling as the attack surface created by vibe-coded applications and hasty AI deployments generates no shortage of targets. Whether these tools can keep pace with the vulnerability creation rate remains the open question of 2026. The broader threat landscape reinforces why software supply chains and network trust models need rethinking. The Kimwolf botnet has infested an estimated 1.8 million Android TV boxes, cheap, unbranded devices manufactured with zero security oversight and often shipped with malware at the factory. These devices sit on home Wi-Fi networks alongside corporate laptops, turning remote work environments into hostile operational theaters. The botnet mines crypto, sells bandwidth, and provides persistent network access, all while the device owner thinks they're just watching pirated movies. The editorial argues convincingly that the castle and moat security model is dead, and that SACE, Secure Access Service Edge, architectures represent the only viable path forward. On the offensive tooling side, Pentest Agent, an open-source AI agent framework for black box security testing, appeared on GitHub this week, supporting bug bounty, red team, and penetration testing workflows. Another example of AI capabilities diffusing into the security toolchain. AI system design and behavioral verification. As AI systems grow more complex, fleets of coding agents, multi-agent swarms, always-on security scanners, the question of how to verify that these systems actually behave correctly becomes increasingly urgent. Roivan Cohen published a provocative LinkedIn post arguing that most intelligent systems fail because they leave the world, think about it, then try to return as if nothing changed. His proposed solution involves temporal AI, intelligence as a dense field of self-learning loops operating over a structural world model where memory is not history but structure in motion. He envisions loop densities ranging from thousands per second at millisecond timescales to billions at nanosecond timescales, with forthcoming AI appliances and chips sustaining this at wire speed. The vision is grand: intelligent systems that behave like nervous systems, mostly quiet, reflex-driven, instantly responsive when boundaries are crossed. But commenters rightly noted the gap between aspiration and falsifiable claims. One asked pointedly, "Why are you burying it in unfalsifiable prose? And why are you talking about femtosecond timescales in relation to computation? That is a conceptual error." The underlying intuition that continuous feedback loops outperform batch process return cycles has merit in control theory. But the leap to nanosecond AI learning loops, running on custom chips, remains firmly in the extraordinary claims require extraordinary evidence category. A more grounded take on continuous verification came from Ikenna Okpala's editorial on continuous behavioral verification, CBV, an always-on verification layer for multi-agent development systems. The core problem is precise and real. When multiple AI agents build software in parallel, the code works. Is not the same as the product works, and this gap widens with agent count. Okpala's experience with Claude Flow, a multi-agent orchestration system using Spark methodology, revealed that the biggest failure point occurs between architecture and implementation. Without intermediate artifacts, interface contracts, shared type schemas, event catalogs, parallel agents will happily build 8 bounded contexts that are each correct locally and incompatible globally, turning integration into a week-long forensic exercise. The proposed solution involves 5 machine-readable intermediate artifacts: OpenAPI specs, shared types, event schemas, error catalogs, and contract tests that constrain agent behavior and enable continuous verification against specifications. This is the kind of methodological infrastructure that separates toy demos from production systems, and it's exactly what's missing from most vibe-coded projects making headlines. Specialized AI applications. The expanding frontier of specialized AI applications continues to generate both practical tools and integration challenges. On the creative tooling side, Hartmula Comfy UI brings AI music generation and text transcription into Comfy UI's node-based workflow system, joining a growing ecosystem of specialized nodes for text-to-speech using Kokoro TTS, advanced motion and animation for video processing with Hunyuan Video, and image layer manipulation with Qwen models. Meanwhile, the embodied Claude project from a researcher with a PhD in engineering explores giving Claude a physical world interface through a DSL, domain-specific language approach, though details remain sparse from the repository preview. On the practical side, a Reddit user's seemingly simple question, asking for help with local PDF and image extraction on Windows 11 with 32 GB RAM and an RTX 2090, highlights an underappreciated truth about specialized AI applications. The gap between "a model can do this" and "here's how to actually set it up for your specific hardware and use case" remains substantial. Document extraction in particular sits at an awkward intersection of vision models, OCR, layout analysis, and structured output, tasks where no single model excels at everything and where the right answer depends heavily on document type, quality, and downstream requirements. This is the mundane reality of AI adoption, not breakthroughs in reasoning or security research, but the unglamorous work of matching capabilities to constraints on real hardware.